Chapter 3, Digital Logical Level, Lecture 3, BUS, Computer System Organization. Today, we are going to continue our talk about Chapter 3, the logic design. So it's actually the logic design level. But here, we are starting to talk about the CPU chip. So what is this topic related to the previous one? The previous one, we talk about CPU. Inside the CPU, how a different gate being designed, the D latch, SR latch, and logic design, how to use the inverter, NAND gate, NOR gate, those kind of things, okay? To do the computation part for CPU, and we also talk about the memory, dynamic memory, and then self-coupled SRAM, okay? Something like that. Today, we are going to talk about different features about chips. And chip, actually, we are talking about the interfaces. So we pretty much talk about the bus. How you ship data out from your chip. And then where are they going? Also, how are they going to be connected? And how they get the control of the buses. So here, you talk about the pin now. The power pins, the data pins, the control pins, different pin now. And also we talk about the bus controller. We talk about the I/O part. We talk about the memory and then how to gain the access to the bus. These three different things. So basically, if we look at the system board, so we will look at the motherboard. So here we have a motherboard. So this motherboard, actually, we talk about the processor already. And now the memory card over there, and then I/O cards. So there's a PCI Express. And then there's a system bus controller or something. So we need to talk about these different peripherals and the I/Os and the memory and the CPU, how the whole system got organized. That's what we want to do today. And then let me bring up a chart. So basically, we finished this memory organization for 4x3 memory. And then now we are talking about something bigger. Actually, we are talking about the CPU chip. So the CPU chip, actually, you have a bus arbitration. And bus arbitration, I say, is to get the control of the bus. So you have the CPU, and you may have more than one, 2, 3, or 4 of them. And you may have memory. You may have I/O device. And these several different devices or chips, they are connected by a bus, right? So in that case, actually, it is impossible, like, okay, it's just like in a classroom. Somebody try to talk, but they cannot talk at the same time. Is that okay, Eric?
So only one can talk at a time?
Of course, you are sharing the bus. So if I am sending data on there, somebody there's only one guy can.
Already occupied?
Yeah, occupied. It's just like a radio or a channel when you talk. You cannot.
CPU to the memory? Is that what you said?
It's a CPU to memory or I/O to CPU. There's only one guy that can control the bus. If there is one bus, sometimes they have more than one bus, 2 or 3 bus. If there's only one bus, that bus actually only one guy can get on. So that's controlled by this bus arbitration. So CPU may make requests to the bus controller and saying, okay, am I okay to send data now? And then the bus controller will say, okay, nobody is taking it. Okay, you know what I'm saying? Mm-hmm. Or maybe the 64-bit. They chop into 32-bit. One guy used the 32-bit up, the other guy used the lower 32-bit. So there's some arbitration going on. And then this CPU also need to have the agency, how you access the data. So basically, there's a bus control, that's sent to the controller, arbitrations in the controller, and the agent is actually connected to the address bus. So there is a control bus, address bus, and data bus, right? So basically this CPU, you will need to gain the control by negotiating with the bus arbitration, and then you send out the control like read or write over there, and then you also need to send the address pins data to in order to access some different data, and your data also being loaded to there in order to send the data over. Okay, and then this chip also have some clock coming, and then basically you have a clock coming to here as well. And what are the interrupts? What are the interrupts? Interrupt is actually from I/O usually. Okay, so basically if I need to load some data to my memory, or I need to print out something to my monitor terminal, my interrupt is doing that. Or I need to read data from my hard disk to memory. Those kind of things are actually put into the interrupts. Is that okay? And then there are some co-processors. Yeah. What are the co-processors? Co-processors, like here, you have a CPU. Say right here, you have a CPU, right? And for example, I need to do some graphics. So I have something called GPU, graphic processing unit. So that guy actually do the graph processing much faster. Or recently, you have the AI tensor processor unit. Or in the past, people use the floating point processing unit. So for floating point number, it will calculate faster. Those are called co-processors. Is that okay? So these are the main
processors are used to help
to make the calculation faster. Because inside your CPU, you only have one single ALU. So that's the integer to integer operation. So usually this ALU, we call it IPU, integer processing unit. So for floating point number, floating point has different data formats. So when you do multiplication or adding or something, it actually needs special format. Is that okay? And then GPU for graphics, say I'm printing out some picture. And those are picture loading or processing. I'm trying to actually process the picture to do, for example, apply some filter on it. And then that graphic processor can process much faster than your floating point unit or integer unit. And recently, this GPU from NVIDIA even grouping the AI function into there, because some of the pattern recognition, like face recognition, will be there. Okay, will be also grouped to the GPU. So let's try to look at those things that are internet. So if you go to Google and you type NVIDIA GPU with AI, so here you will see NVIDIA AI computing company. Okay, NVIDIA used to just provide those GPU, graphic processing unit. And now NVIDIA itself calls itself AI computing company. So what's that? Usually you have a GPU computing per performance, right? And actually it try to increase the GPU by adding the AI feature into there. Okay, and AI do a lot of things. Actually will help pattern recognition. So it start to do the AI stage, try to add those AI onto helping diagnosis of the medical, say, self-driving car, taking the picture from the video and then recognize, is that a person or is that a dog or is that actually something else. So recently there's an accident just happened, like there's an Uber car. The Uber car come with this kind of face of people recognition system, but it failed to recognize the person, a woman, as a person, and it just hit it because it saw that it's just some block or something, trying to hit that away. So there is a self-driving Uber kill Arizona woman in first photo crash involving the autopiloting and the recognition. So that part is very important. Okay. Recently, it just happened like a self-driving Uber driving on the road, and then Arizona woman is the first person got killed by a Uber car. And then when they actually investigate the problem, and then they find out, okay, the car comes with some graphic processor, and those processors, I didn't say that it's actually from NVIDIA. I don't know what vendor for the processor, but that processor just failed to recognize the person as a person, and then it just hit into it. It saw that it's some sort of garbage or blocking the road. Is that okay? But here, I just trying to say that this kind of technology right now, embedded system right now is very hard. Okay, very hard. Autopiloting. So this field actually is also one of the fast-growing field to do computer architecture or embedded system. It's still quite fast-growing. So don't look at just like meat processor. That's actually history. Okay, that's actually history. If you want to do project in here, it's also a good career to pursue for. Okay, so that's the CPU and the bus CPU chip. So each CPU chip, you have those different interfaces. Okay, so basically a CPU, you have a few things you need to remember. M and a N. If you have M bit address, you will be able to address how many location of the memory. You can address 2 to the power M, right? So 32 bit, you can address 2 to the power 32 bytes of data, and that actually is 4 giga. Okay, 2 to the power 10 roughly is like 1K, 1000. So 2 to the power 30 actually is 1 giga, right? And then 2 to the power 32 will be 4 giga. So 32 bit give you the 4 gig address space. But now this 32 bit address space is not enough. So people start to use the 64 bit. Okay, because the memory now is actually way bigger than that. Okay, and then the other number is the N number, is the N bit words that actually is a bus width. So the address pin, you have that M number that give you the 2 to the power M memory address. So that's when your address, you actually have that 2 to the power M different location of my memory. And then the 64 bit are here. Say you have N bit, A bit, 32 bit, 64 bit. The bus width is a number of bits that you can read out from here and ship the data out. Is that okay?
Yeah.
That's the N number. So let's go back to the chart that we see last time. So basically, that is related to, okay, it actually is related to this one. Right here, this 2 bit, right? So 2 bit actually is like 4 data location. Here, output is 3 bit, right? So this is the N number, right? So here, this is N, and this one is the M. The A1 and A0, M is equal to, right? Here, N equals 3. Is that okay? If you look at this a chart, it's what we talk about, a very miniature memory model for that, okay? So basically here is the, okay, so the memory structure. And then you have the, when you do output, there's a tri-state buffer, right? When you at the last stage. So the tri-state buffer actually is like, I have like, say 64 bit or a lot of bit, right? And everyone connected to a same bus. Everyone's connected to a same bus, say certain different option connect to the same bus, right? So for example, this one may be from CPU, this one may be from memory or something, right? Everyone's connected to the same bus. So if I don't have the release signal, this one actually is just like off. So it's actually floating. Okay? And if this one got enabled, the data will be flowing through and take control of the bus. Is that okay? So basically, if it is off, it's just like open. Okay, so that's why tri-state buffer I say is quite important. When it actually accesses the bus, it actually needs something like this. Okay, so a memory chip, you have this much data. So right here, as you can see, the HS bit is what? 19 bit, right? 0 to 18 is 19 bit. So you give you 2 to the power 19. That's what? That's a 512 kbytes, right? That's 500 k. So 2 to the power 10 actually is a k, right? 2 to the power 9 is a 512. So this number conversion binary, you need to be very fast. So you know what is the size of the memory real quick. And after that, you have 8-bit data, right? That's 8-bit data. So it's a 512 3A times 3A memory. A is 8-bit, okay? So here you have 3 control signal. This one is clock stroke. And with bar, it means low enable. Well, what does low enable do again? If you have a bar, and what's the difference between low enable and high enable? Still remember that? Last time I discussed this, the low enable signal. When you see some signal that come with bar, it actually is a low enable.
It's inverted?
It's kind of, say if I have a logic, like AND gate, this one is high enable, so the data will flow through when it actually is high, right?
When it's low, it's
and
floating?
If I use the OR gate, this one is like low enable, because when you have 0, the data will flow through. Otherwise, it will be hold to high. Is that okay? Is that okay? So basically, low enables means the data only enable at the low clock age. So only this portion, this is active. The chip outright or output is enabled. So here we have 2 different signals. So if the write enable is low, this is low enable write. This is output enable, right? So here, if I hold my output enable to be high, my clock stroke actually is like this, low enable. So basically, only in this period of time, I'm trying to write something, but my output enable actually is hold to high, and is low enable, so high voltage actually is not going to output. At that time, I'm going to put the data into my chip. That's the write enable. Write enable bar. That's the low enable the write. Is that okay? And if my signal is like WE instead of having the bar on it, it's called high enable. That means my control signal, only when it is high, I'm writing data into my chip. Is that okay? Is that okay or no?
Yes.
So remember here, high or low, with bar or without bar, it just means the polarity of your signal. It just means the polarity of your signal. Whether I'm enabled by 1 or I'm enabled by 0. So here, if you have a signal, say this one, I want to write something out to the bus, right? So my signal, if my low enable, the output enable, is actually holding high, that means no data will be coming out. No, there's no data will come out. Only when your signal actually pull down, when your signal actually pull down, at this time you will be enabling the output, right? But if your clock strobe not arriving, it won't actually enable the data. So the clock strobe need to be going low also in order to put the data out to the bus. Okay, so output enable and clock strobe, which one should be wider?
What?
Output enable signal and clock strobe, which one should be wider?
Output.
Yeah, because you need to make sure that when you try to strop the data out, your output enable need to be there. Say if your class strop is like this, right, and your output enable is smaller, the data cannot be write out safely because the data over here.
You only get part of it, right?
Yeah, you only get part of it. Yeah, exactly. You know what I'm saying? So this is a timing spec you need to follow. Okay, on the right hand side we have this address that is actually 11-bit, right? 11-bit, and this one actually is 1. It's actually by bit, 1 bit only, 1 bit output. So it say like 10 to the power what? 10 to the power 2 to the power 11, right? But it says that it's actually 14 something 3 memory 4 megabit. And this one is also 4 megabit, right? And how comes here it actually here is actually different data. Why this only 11-bit, but its address space is bigger than this guy that is 512. Okay. It only have 11-bit, but this guy has 19-bit. How come this is bigger? Bigger by how much? 4092 divided by 512
times 8.
8 times, right? 8 times bigger. So it has 3 bit more. So if this one is 19-bit, this one effectively should be 22-bit. Right?
Yeah.
Why? Why is address has fewer, and then here actually has larger memory space? That's because it has the row address chop and column address chop. So this one RAS is called row address chop. And this one CAS is called column address chop. What's that? So now let's look at the memory cycles. So the first thing is like, this is low enable, right? So my RAS will go low, right? And then I will need to have my address pin. So this address pin is from 0 to 10, right? My address pin must be ready during this period of time. So some data are there, right? And then my clock stroke will be something like this, right? Keep stroking, okay, keep stroking. I cannot exactly show the clock clearly, but keep stroking. So what happened is like, right here, when there's a low enable edge, right? My row address, 11-bit being stroked into my row address. And my row address is row 0 to 11, right? After that, I will send another signal, will be after this. I will send another signal called column address stroke, right? And then my A again, let me write it 10 to 0, okay? So it actually will show better. The address will be stroked in, so the address got stroked. Some clock edge, it was stroking data, and that data got stroked to this column. So we use the row address and column address. So row address 11-bit with column address 11-bit. Totally, I have 22-bit. That is my address. So I use two stroke cycle to stroke my address in. But I only have 1 bit output. So each of the address only access 1 bit. And right here on the left hand side, it actually has 8 bit, so 1 byte on each memory location. So after that, I have my edges ready, right? After that, I have my edges ready after this cycle here, right? After that, I give you another, I say this time, let me give output stroke, output enable, right? And then I have my certain clock stroke. So my data will be released over here. So my data D will be stroked out at that time. So this one, whatever I'm showing right here, is called memory access cycle. So to access a memory, you need to put your edges ready, and then you enable your output enable or write enable. You know what I'm saying? But if your address is more than the pin that you can handle, the total pin you can handle, then you actually need to stroke in by 2 times or 3 times. Is that okay? Is that okay? So
Yes.
first one actually is you only have one address. 19 bits, 19 bits. So that one you don't need to use the column stroke and row stroke. And the second one you need that because each time you only have one signal to stroke in the data. And that kind of organization about when to stroke in the data is called memory access cycle. Is that okay? That is called a memory access cycle. So this part you must be listen very carefully, okay? Otherwise you can do it. And now here, this guy is more complicated now. It actually has bank 1, bank 2 selector. What's that? So here it said that 32 mega, right? So you totally, now you have 13 bit, right? So you have 2 to the 13 times 2 to the 13, right? Because we learned that will give you 26 edges bit by 2 stroke, row stroke and column stroke, right? So how many of that? How many of that? That actually 26 will be 2 to the power 20 will be 1 mega. So this one totally is 32 mega. Right? So 32 mega times 16 bit give you 2 to the power 5 times 2 to the power 4 give you 2 to the power 9. So this one totally is 512 megabit. Right? It's a 512 megabit. Then what is the control for bank 1, bank 2 now? What is the control for bank 1, bank 2 now? That's because I can have this one 512 megabit, 512 megabit, and then this one enabled by bank 0, and this one enabled by bank 1. So when bank 0 is active, this one got selected. When bank 1 is selected, this one got selected.
What do they do?
You can select different bank.
Yeah, what do banks do?
What?
What do banks do?
Select whether the chip got selected or not. So the previous two memory organizations that whatever address I loaded in, that will be selected, right? But right here, actually, it will depend on whether the bank got selected or not. Otherwise, the chip still not going to release data or write data in. Is that okay? So memory, you have the SRAM, DRAM, SDRAM, different type of RAM, ROM, read-only memory. So read-only memory, you cannot write. You can only read. Okay? ROM is programmable, that you can initially program it, but you cannot, after that, you can only read data out. Okay? And EEPROM, electronically programmable ROM. Okay? So that actually programmable. So mostly these differences read mostly, but you can program like maybe every year update the software or something. As for double EEPROM. On the field, you can actually program it. Okay? PROM is actually not on the field. When you actually build a machine, you can program it. ROM is that you no programming at all. You have to build it when you are manufacturing it. It will be born. Is that okay? So these are different non-volatile, and then it's go back to CPU. Now, here are the buses we are going to discuss. You have the register bus, ALU. So there is one bus, on-chip bus, and actually on-chip bus is faster than the off-chip bus, I/O bus, memory bus. So there are several different buses to be controlled, and there is a bus controller. Okay, conceptually, is only the chips are connected to the 3 bus, but physically, actually, it's not. Actually, you talk to the bus first. You talk to the bus controller first in order to make sure that you gain the arbitration, and then you actually have the control for certain bus. Is that okay?
Yeah.
And then here you have the register. So right here, for example, my ALU result, I want to write back to 32-bit, 32 register over there. So I need at least 5-bit to access my register. So my register actually got lined up like this, each one 32-bit, right? So N is 32, right? But my M is 5 right now. So I have 2 to the power 5 different location, and I need to have the right 5-bit decoded to access the right register so that I can actually use the bus to write the data into the register I want to write. So that's what this on-chip bus is. Is that okay? But usually on-chip bus is simpler than off-chip bus in the control because it doesn't need a lot of arbitration. So computer buses, you have a CPU memory bus, you have the I/O device bus, you have the coprocessor bus, okay, you have the I/O bus. So CPU can be the bus master, and then I/O can also be the bus master, and the slave. What is a slave, and actually what is the master for a bus? That is because that if I have a CPU, right, and here I have my memory, right. So I want to write or read data to memory. Basically, I'm using my CPU to drive.
Wait, I don't hear anything. I'm lagging.
Okay. Let me repeat again. So what is the master and what is slave for a bus? So for example, if I want to write something from my CPU to my memory, then my CPU will actually arbitrate for the control for the bus. My CPU will put my address over there. My CPU would actually get data from bus or load data to bus. Then my CPU is the master. My memory only actually follow my CPU's instruction on the bus. So at that time, my CPU is the master. Is that okay? Is that okay so far?
Yes.
And so basically, memory don't initiate the bus transaction by itself. As you can see, main master for bus is CPU, I/O, or coprocessor. Is that okay?
Yeah.
So memory actually mostly are passive device. Actually follow some other people's instruction. So let's go back to our book. So basically, a CPU, you have those different things: bus controller, bus interrupt, bus arbitration, coprocessor signaling, status, and miscellaneous. So this portion we finished. Then the next one is bus. So here it has the definition for a bus. So the bus here is like, it said that a bus is a common electrical pathway between multiple devices. So it's just like a highway. And compared to highway may not be that accurate because highway you can have several cars on it, okay? So usually I would say it's actually a trail. Railroad, I'm sorry. I would like to say it's a railway. You know why? Because on the railroad, only one car can travel on it. right? And then if you need to actually escape from some other car, you need to go off pass, stay right there until the other car pass, and then you can come back, right? So there's some arbitration need to go on. So it's work more like a railway. Less than a freeway. It's not a freeway. Everybody just jump on the rail. Jam is jam. I don't care. I can go on. That's actually more different. Is that okay?
Yeah.
And that's probably also the reason why it is called bus, because you actually jump onto a bus and then you can actually ride it. Okay, you can actually ride on the bus. So here you have the system bus, you have the IO bus, you have the on-chip bus. Okay. And each bus has its own protocol. Each bus has its own protocol, and the protocol is used to arbitrate who will gain property. Okay, and also electrical and medical property. Say my bus high is like 5 volt or 3 volt or 1.2 volt. Those are called electrical and mechanical spec. So CPU may be made by say Intel, right? And the bus controller bridge, so north bridge, south bridge, may be made by VIA. Okay, memory may be made by Samsung. So it's not like one company. So these different guys all need to talk to the bus. So bus has standard.
Do people make buses too?
It's mostly the chipsets. Mostly the chipsets. So there's a chipset company doing that. Intel is a big chipset vendor as well, and VIA is also a big chipset vendor. So here, like, let me show you. So for example, Intel has chipset, right? And how to here even somebody teach you how to choose a chipset. Okay, so you need to find when you buy this different chipset and you try to actually assemble a game station, say, right? MSI also provide a different ASUS, MSI, they all provide these. Okay, and then you have get the right socket for your CPU, small board, and then basic chipset, board size, and port. So when you assemble your own game station, you got to know what board am I working on, okay? And am I using the micro ATX or mini ITX chipset? Okay, and then are you running the USB or running USB 2 or 3? HDMI differences, okay? So there are a lot of spec you need to check in order to buy the right one for you and make sure that it talk to your system, your CPU. So for example, Intel itself is a big chipset company. It not only give you so it actually has the desktop chipset, and that chipset actually controlling the whole bus and whole. It's probably more important than the CPU itself. So here you can see that you can like this chipset controlling 14 different USB, 24 PCI Express.
What does that mean?
Okay, so that means like.
So if I want to upgrade my computer, would I buy a chipset or would I get like a processor?
Actually, no. Usually, your chipset is actually you can upgrade it. You may have a socket. So what happens is that you have a CPU, say i7, right? And then here I have my memory. So memory, I have it on card. I can insert more card onto it, right? And then there is the IO bus. So the chipset actually controlling like, okay, this motherboard I make, how many USB I can have. And if you use for smaller USB, then you cannot handle it. So the IO device cannot handle that much. So that chipset need to work with your CPU to decide your board. But once you buy a motherboard, The chipset pretty much there. So you need to use the right motherboard with the right chipset. But once the motherboard designer already designed a motherboard, basically you are tied to, because it's already in there. It's already in there. So here you have the CPU, right? So here, but here you have the ASUS chipset. Okay? That is the motherboard, it has the ASUS chipset. And what does the chipset do? The chipset actually provide a control for this USB, PCI Express, and your memory. So that's some sort of like your controller of the buses. Somewhat like that. Okay, somewhat like your controller for the system bus. So system bus is more like a academic term. So here I say, okay. So what is chipset? So in the computer system, chipset is a set of electronic component in a integrated circuit form called data flow management system. So where will your data flow from where to where? So that manages data flow between processor memory and peripheral. So it's a CPU, memory, and I/O. Is that okay? And it's usually found on the motherboard. So chipset actually is the bus controller. Is that okay? So that, okay. Here you have this one called processor, chip RAM, fast RAM. So chipset actually can control further I/O, audio, or video. So chipset actually is the controller for the bus, controller for the I/O, controller for everything on the chip. So academically, we call it bus controller, but chipset actually more than that. Actually, it's more powerful than it. So here you have the GPU from ATI. Okay, ATI is one company. There's a CPU. There's an NB. There's an SB. There's an NB. There's an SB. Both of this guy and this guy, both are chipsets. This one SB is called South Bridge. This one NB is called North Bridge. But can you actually replace the chipset? No, actually burned onto your chip, your board already. So if you want to buy a powerful machine, you have to find the right motherboard that comes with the good chipset for you. Instead of, you cannot take it out. CPU actually you can upgrade. You can actually, there's a socket. You can actually take the CPU out. But not a...
Yeah, my friends like to upgrade a lot.
Yeah. Memory, you can use an add-on card to upgrade it. You know what I'm saying? Memory, you can use an add-on card to upgrade it. Especially for the game player, you know, for like half a year, 2 years later, okay, my memory is too small. I have to buy some more memory for it. Or my CPU not fast enough. So
What's
basically,
the problem with small memory? Is it like
you
just want to download more games, or is it
well,
or does it slow down your computer when you don't have as much?
It actually will actually for memory, I think sometimes is if the program is bigger or something, the more memory it actually will be faster. More memory will be faster. So here you can do like, okay. So it actually told you how to install a CPU to your motherboard.
This is Ranjit from TechToBats.com, and in this video we're going to install Intel processor on this motherboard, and the motherboard that you're seeing is an Asus.
Right. So this is one kind of upgrade, right?
Both the Sandy Bridge and the Ivy Bridge chips based on the LGA socket 115.
Is that okay?
And I'm going to use.
Okay, and also you can actually install, or you say,
if your computer seems slow, you can upgrade your RAM and make it much faster. If you're thinking about buying a new computer, you can save yourself a couple of $100 by buying it with the least amount of memory and then upgrading the RAM.
So this kind of tower thing is actually for experts. Okay, those guys who actually want to do things well, like big game station. So that's why the tower usually is really big. So you can actually put it out.
So like the computer I have is too small.
I couldn't say it's too small. Actually, it's not too much upgradable. You know what I'm saying?
So I can't really upgrade this.
I would say yes, you can upgrade something, but not a lot.
So what I typically do is I go to Amazon and I look for DDR.
So the tower thing actually you can even change the motherboard, right? You can actually change the motherboard as well. You can buy a new motherboard, keep the keep your hard disk, keep your whatever component you have, even CPU, right? Right, but here you say this guy try to connect everything, right, and then change the whatever motherboard it is, right? So how to replace motherboard with a new one, right? So he's told you like, okay, how carefully should I strip off my hard disk? How carefully should I strip off my memory board? And then he can find a new board, okay, and then assemble it. You know what I'm saying? So he probably got this one probably the new CPU, and then memory got updated.
If one of these wires like break, it's not gonna work. Right?
What?
That's why you have to be really careful.
Yeah, you need to be careful. If you don't wire it correctly, it's just like you unplug your cell phone from the power supply, and then if you don't connect it back, you don't get power. You know what I'm saying? And if the fan is not installed right, your chip will be too hot. So this actually takes a while to learn how to install it, you know. But whatever, you know, actually you see here, it has some number, like temperature or something, right? And here actually when we go to this, actually two things good for this computer organization is that one thing is need to know about the CPU well, knowing about how to do CPU programming with MIPS or something, right? The assembly. The other one is know about system well. So should I buy this CPU or not? Should I buy this memory or not? Should I buy this PCI Express board or not? Should I buy this kind of fan or not? Should I buy this DVD-ROM or not? Okay, how can I connect all of them together to make my PC better? And then, okay, now my game station too slow. How can I compete? Improve the CPU, that's one thing. Improve the memory loading, that's one thing, right? How come some memory, when you actually upgrade it, it will make difference? Because if you go to here, right, your CPU is not actually doing one thing at a time. It actually has so many processes. Each one takes some memory. So say here, my memory is taken by 54%, right? Hello? So if my memory I improve, the percentage will drop. Once the percentage drop, I can put more process in there, and I actually can do more things at the same time. My person or calculation for my game will be actually faster. You know what I'm saying? So here actually is related to that. And this one here, remember, is just a conceptual diagram. It's just a conceptual diagram. The real controller or memory or this I/O. So it said like the chipset say like 12 USB and then 14 PCI Express. Actually, it's talking about this I/O bus spec, and that guy actually is called bus controller. But you have north bridge and you have a south bridge, and each one is controlling the memory. The other one actually controlling the I/O. Are you okay? What's this? Okay. So that's the different buses you will actually have. And then bus width. Bus width, I talk about, that depends on the edges you have. You have 22-bit edges, 22-bit edges. And then actually, one thing I just told you, right? The number of bits on the out of the chip is different from your memory space. It's different from your memory space because you may have the row stroke and you may have the column stroke. So you may have like 40-bit memory space instead of just 20-bit. Is that okay? Is that okay? So the edges actually is not following the pin. The number of pin is not really what it is. So here you see that 8086, it only has control with 20-bit edges. And then here we have 4-bit edges and a control. And here we have another 20-bit, 4-bit, and then 8-bit control. It's making the control edges bit more. And then what are these 4-bit edges and 8-bit edges for? What are these for? What are these for? These 22 bits they are connected to a chip, right? And that actually has 20-bit edges. But remember that there is a bank selector. So can use the extra 4-bit to say I have, when the vendor memory they don't come with like 4 gig memory or like 16 gig, just exactly the memory size you want. It may say 500 mega, say 5 mega, something like that. Okay, if it's 4 mega, I mean, so 4 mega is cheap, and maybe you need to buy a certain 20 memory chips and then put on the board. And each board may be using the bank selector to see whether that bank being selected or not. Is that okay? But the CPU address is different.
So the 4-bit address is used to check
the banks. Yeah, the different banks. So here actually you can go to like here, and then here you say each chip, there are several chips on a board. So memory are organized like this. You know what I'm saying? Memory are organized like this. So each individual chip is of fixed size, right? And then I can select bank, right? So for example, if my data bus has 32-bit address, 32-bit bus, right? Then each one of them say I have like 1 byte. So here actually for 32-bit bus, actually if each one of these are 8 bits, okay? So 32-bit bus, this whole thing is one bank. So I have the same bank control for each one. Then they will load the data into different bus connection. Right? Something like this. Is that okay? Is that okay?
Mm.
So actually I can actually connect like this. Right? So then 32-bit address I have like this, right? But if my address is only 16-bit for 286 one, okay, sorry, I don't have that many bus. So here, this one becomes bank 0. This one becomes bank 1. So actually this one I have different bank, and connect this one to here, connect this one. So this two will be selected only when bank 1 is selected. Is that okay?
Yeah.
And then if my bus is even smaller, I just have AB bus for 8086. Then each one of them actually is it will be in different bank. So basically, it will become something like this. This one bank 0, bank 1, bank 2, bank 3. It will have separate controller. Is that okay? So this is the same 1 megabyte of memory, and then you have different controller. The chip itself has a bank selector. As a bank selector, and you need to use the one actually to access it. So the CPU itself will also send out different extra pin connection. Depending, these are actually bank selectors. Is that okay? And then the next one is the bus clocking. I call it memory cycle. So let's read this one. Okay, let's read this chart. Let's read this chart. So right here, I need to have my address ready first. So my address is actually ready during this time frame, right? My data only ready right here, so forget about the data. First, I need to be actually making the memory request. So my address ready, so let's show some data to my chips, right?
Mm.
And after that, right, I have my read enable. Right, this one actually is called output enable, but here it's called low active. So it's low active. When it's low, it's active. So actually it's called output enable because for the memory it's actually output enable. But for system bus, it's called read. So this one is read signal, but it's low enable. Okay, here is a wait signal. What is the wait signal for? My bus is not ready, so actually let me send out wait to just cut it. So this one length can be extended. And here say, okay, I'm ready, my memory chip's ready. Okay, then I pull up. Okay, so this one wait is hold on, don't send data out. Hold on. You know what I'm saying? This low enable, this one is hold on right here. Hold on, don't send data. Okay, I'm ready, so pull up high. No more waiting. Right?
Yeah.
And then the memory release the data at this time frame right here, T3, and then the data got read out from the memory. Is that okay? So this is a recycle. This was a memory access recycle. There are a few timing you need to actually to remember. Here are some detail you need to remember. It's a TAD, TM, TML, TRL. This different data you have to read from your book. Okay, you have to read from book. What are the definition of that? I actually said the minimum time I need to have from my class age. I need to have my memory address ready. You know what I'm saying? Because I don't want to, once I erase it, your data actually is unstable part or something. You have to check those different specs from your textbook. Is that okay? So let's go back to the textbook. So this CPU different buses, we have that. And then, okay. Some line they actually connected together, we call it wire old. Some line we call it wire old. So wire old is actually like this tri-state buffer. Okay, we wire together. So the data is 1 only when one of them is 1. If all the 3 release data, it will all be 1. It's called wire old. Wire old. So say I have the in gate, right? And we 3 actually wire together. One of them pull high, the whole thing will be high. It's actually also similar to OR. So that's called wire OR. But wire OR sometimes good, sometimes a bad feature. And then bus width, we talk about it. So here, bus width is the most obvious design parameter. The more address line a bus has, the more memory the CPU address can direct. Okay, if a bus has n-bit address line, then you can address to 2 to the power n different memory location. That's from CPU point of view. So the more bit I can access more memory. But the physical memory may not be grouped as what you actually specify by the n bit. So they may put into different board, they may put into different banks. The problem is that wide bus need more wire than narrow one. They also take up more physical spaces and they need bigger connectors. All of these factors make the bus more expensive. Thus, there's a trade-off between maximum memory size and system cost. A system with 64 lines of edges bus 32 2 to the power 32 bytes of memory will cost more than 32-bit lines of edges and 2 to the power 34 bytes of memory. So too much memory edges bit, it will cost more. Okay. So possible expansion later is not free. You need to pay something. The result of this observation is that many system designers tend to be short-sighted, with unfortunate consequences later. So sometimes when they design, they just, okay, when I design 8088, I just put a 20-bit edges because that's good enough for me for the time being, right? So it only can access 1 megabyte. So that actually 1 megabyte memory is the time when we use IBM XT back to the year 1985. Okay, that's the XT spec. And the first Windows system destroyed by this 386. Okay, at that time the memory space is way bigger, maybe 20 times, 40 times bigger than the 1 mega memory. Okay, so then like 386 came out, another 8 edges line. So it 8 one by one. Okay, first you have 20-bit and then 4-bit and then 8-bit edges along with still more control lines. Okay, the resulting design is much more messier. So because they don't have the good prediction on the memory side, so actually just, okay, that's 8 more bit. Okay, that's 8 more bit. And that's called incremental design. So incremental design sometimes good, sometimes bad. Incremental design. Incremental design means my original chip. Okay, I give the 8-bit edges. Okay, not enough. Let's put another 4-bit. Okay, not enough. Let's actually put another 16-bit. You know, so actually it's not well thought of design. That's called incremental design. And then to a certain version, you can no longer like that. You have to do re-innovation design. Okay. Not only does the number of edges line tend to grow over time, but so does the number of data line. Albeit for a different reasons. There are 2 ways to increase the bandwidth of bus, decrease the cycle bus. So actually you can decrease the clock time. And that actually depends on the system fabrication technology, whether the smaller clock time is possible or not. And then the other one is speed up the bus, and a problem called bus skew. Okay, because the signal with different line travel slightly different, it's called bus skew. What is bus skew? Bus skew is like, I have a clock, right? I have a clock sending out signal, but my D0 bit, I'm assuming that my data will be, say, released over here, right? But actually my D1 bit, actually I'm supposed to do on the same time to be valid at the same time. But sorry, this one may be actually ahead a little bit. Okay, and then there's a D2 signal maybe, okay, it actually trail by a little bit. And this, because of the bus have the bus skew, this can never be at the same time location. And with that, you have to be designing your system quite carefully. And that's actually one factor to determine how fast can you drive your bus. The clock, you want to speed up the clock, so the clock signal a little bit smaller, that would be better because it's actually faster. But because of the bus skew, you cannot actually take arbitrarily small clock. Is that okay?
Uh-huh.
So that's another problem for speeding up that. And then to get around the problem is of very wide bus. So wider the bus, actually you would actually end up more problem. So sometimes designer opt for a multiplex bus. So basically, instead of using the 64-bit bus, let me do this data 32-bit at a time, and then next time I put another 32-bit. So that's called multiplex the bus, okay? And then bus clocking. Bus clocking, you have the synchronous bus and asynchronous bus. So what is actually the synchronous bus? What is the asynchronous bus? Synchronous bus means everything are in clock cycle. So my clock is right here, right? So your edges need to be here, 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 somewhere according to the clock, or with some small time delay or leading, that's fine. That's called synchronous clock bus. So what is a synchronous bus? A synchronous bus is like, I don't care about your this different, I don't care about your buses. I don't care about a clock. So here I have a memory request. And then I have a memory request. And then the other guy say, okay, I hear you. I can send out data. So this is a request for memory. And the other guy will send out a chronology signal. Okay, I can send out. Okay, and then the next one, the system send out the data over here. And once the data got received, okay, I'll turn down something. So when there is no clock, we call it a synchronous design. Is that okay? When there is no signal actually receiving, is asynchronous time. So usually right now, most of the computer systems are synchronous. And something like what is phone may be asynchronous because I don't know when am I going to get my data. So more slower system use asynchronous design. So if I get some data, but actually I don't get the data I want, it will insert the wait state, extra bus cycles, until the memory is finished and negate the wait state. So some memory, I'm trying to write it, but my memory is so busy, sorry, you wait. So actually the bus controller will send out the wait signal. Don't move, okay? It's taken by other people. Is that okay? So that's what it is. So here you have this different spec. So here you have TAD, the HS output delay, okay? So it actually means that once my clock edge right here, my edges were available after a certain delay. So here maximum, I can only tolerate 4 nanoseconds. Is that okay? So these are some spec requirement that the designer of the chip or the system need to know that you need to support it. Is that okay? Hello, is that okay?
Yes.
So I don't go into those details for these different parameters. Okay, and asynchronous bus, as I told you, it's not by clocking. It's by you wake me up, I wake you up type of things. You know. So basically, asynchronous bus is like now. Okay, it's not like okay. Let's get started. Synchronous system is like okay. Let's have the class meeting. Like 9 o'clock, right? And then we will meet at 9 o'clock and then dismiss on 11 o'clock. That's actually more like a synchronous system. A synchronous system is like, okay, you send out an email, can you take my class? And then the other guy say, okay, I'm free. And then, okay, I'll send you the zoom.us link. And the other guy, okay, I got it, I'm logged in now. You know, those kind of handshaking system, you don't have clock. It's all done by handshaking. It's called a synchronous bus. And whether it's called synchronous or asynchronous or using handshaking, these are called bus protocols. The standard way of doing things called protocols, right? It's called protocols. So you have the synchronous bus, you have asynchronous bus. That's called protocols. How the system will be controlled. will be run. Okay, so here you have this different parameter. You have asynchronous bus, and then here the next one's bus arbitration. Okay, so basically I have 5 different I/O devices, and some guy may send a request to arbitrator, but only one guy will be granted. Okay, so they will have round robin master. They may be round robin master. They may be prioritized. Okay, so what is round robin? There are several protocols. For this who will get the control for bus. So here, let's say okay, you type the round robin bus arbitrator. Okay, and there are some guy actually do this already. Okay. Okay, and anyway, we are not going to go into here detailed design over here. Okay, so here actually there's a round robin arbitrator, and it has different states. So I don't go into those details for that, but the key point is round robin arbitrator would determine who will have the control for the bus. So bus requests arrive at the input this. If a bus is free, one of the 4 grant line will be granted, right? For sure. But they will actually take turns. So just like round robin competition, when you go into the Taekwondo competition, right? I fight actually 1 and then 2 and then 3 and then 4 and then 5. You know what I'm saying? That's called round robin. It's not like single elimination. You actually play 1 by 1. Is that okay?
Mm-hmm.
Same thing for this bus granting. Okay, I have 5 I/O device, so I go round robin. This time I go this, this time I go this, and then this time I go this. That's called round robin. Okay, that's called round robin. And then prioritize is different. Prioritize means okay, I have request level 1 and level 2. Okay, let me serve the first class people first. And then second level, okay, if I don't have the first class of people, I serve for the business class. Okay, the next one, okay, if my business class has no customer, then I serve the coach class. Is that okay? Is that okay? Just like the airplane, okay? So you have the bus request busy and then arbitration line, okay, something like that. So here actually you have the different bus operation here. So here actually, as you can see right here, you can have the address coming in and then you send out the data, how many data bytes you need to have, and then 1 by 1 you read the data out. So the data may not be read out in single cycle, say 32-bit altogether got sent out. No, sometimes it's like 8-bit 1 cycle, another 8-bit 1 cycle, another 7-bit, and then continue quite many cycles. So there's maybe in the beginning you need to send out how many count I have. So the address bars, I shove in the address. So the address is stored in my chip. So I know which bank I'm going to select, what row, what color I'm going to take. But because I may have a 64-bit, but my bus only have say 8-bit, 1 byte. Then what? I need to take a clock cycle in order to ship out all my data. You know what I'm saying? So there's a block transfer. Actually, this one block transfer sometimes is like bigger, like 512K, and then I actually put the data and transfer more. What are these block transfer for? Usually, this block transfer sometimes is good for programs. So what program actually you actually want to have this? Say I have a CPU, right? I have a CPU. I have my memory. And in my memory, I have an instruction section. I have my data section, I have my stack section, right? So my program assembly or machine code is down here, right? But my CPU, if I say my program counter one, okay, go there, get one, come back, decoder, and then decide, that actually will be too slow. And also, it's not efficient because clock in the CPU run faster than the memory. So what I would do is actually, okay, here I have a cache. Sometimes cache just use this one, simple, okay. And what I would do is like, okay, I load the whole block of say 512K code from my instruction set and put into my cache. And then I access my memory completely from my cache or from my memory. Okay, completely from my cache or from memory. So at that time, actually, I'm purely getting instruction just on the cache. And in order to facilitate that, I actually read out a whole block of code into my cache memory, 512K code at a time, whole block being loaded. That's called block transfer. Is that okay? Usually it's for big chunk of data or for program. You need a block transfer. Or you just have a memory just store a variable X or Y. That actually is not block transfer. Is that okay? So here is the interrupt controller. Interrupt controller is for I/O devices. I/O devices. So basically, the interrupt controller, it also has the read-write control strobe, those kind of control signal, right? It also has the also have the data pin and also have the address pin. So I/O has two types. I/O has two types. I/O has one type of I/O mapped to I/O. And the other type is called memory mapped to I/O. Okay, write this down, okay? You have two types of memory I/O type. One is called I/O mapped I/O. The other type is called memory mapped I/O. Okay? And they may be using this 8259A is for PC, personal computer, okay? Personal computer use that. And there is a different interrupt register, 0, 1, 2, 3, 4, 5, whatever. Okay, this is 8259A is a real processor in PC, okay? Real chip, okay? It's not fake. It's not dummy, okay? Now, let's talk about what's I/O mapped, memory mapped I/O. Okay, memory mapped I/O is quite easy to understand. So I want to write to my video card, say, right? So actually, what I want to do is like, I have my CPU, right? So my CPU actually write my data to memory with a certain address, right? But here I have my video card. I also want to use that to display to my monitor. So I send out similar address to that video card. And now those addresses, just like I'm sending data to memory. So that actually is called memory mapped I/O because my I/O devices are just behave like my memory. So I write my data to that memory location, and then my I/O device will be able to get the data and then write out to monitor, or I can actually read from my I/O device, say my keyboard, from the memory location and send back to CPU. That's called memory mapped I/O. Is that okay? That's one way to do I/O. Just treat your I/O device like your memory. It's called memory mapped I/O. You have processor, you have bus, you have assembly line, low controller. Actually send out the address just like you send out address to memory. That's called memory mapped I/O. Okay, so you reserve some range of the space for I/O in the memory space. So the advantage is how we're using memory I/O and read-write need to develop a signal, whatever. Okay, Disadvantage is a portion of memory space is used for I/O device. So the I/O device is not of the same speed as memory because it's usually it's different speed. Is that okay? So memory I/O just use your memory, use your I/O like your memory. What's I/O mapped I/O? I/O memory I/O is different. Say you have different spaces. So now I pick a certain I/O register or I/O device by myself. So PC actually is more like a isolated the I/O mapped I/O. So basically, I'm using a I/O register and use that I/O register to access my I/O device instead of writing my data to my certain memory location, and those memory locations actually are fake. They are not really I/O devices. They are actually memories. Is that okay? So I/O mapped I/O is use the I/O with its own controller, its own edges. Okay, so these two parts, I mean, are very important for memory mapped I/O and I/O mapped I/O. They are quite important. Okay. So this 8259A actually are real thing. It's not fake. It has been used for a while. Whether it's still in use or not, I'm not sure. I'm not sure whether it's still in use. I suppose not. Okay, so this one actually is a 5259A I/O block. So when you actually try to use this one, you need to use the interrupt instruction. So in your okay. So in 8086, it actually has the interrupt instruction. So it actually has an interrupt instruction, and the interrupt instruction is used to call I/O. So here it has instruction called I/O. So MIPS it doesn't call it interrupt, or it actually calls system call. Remember that? It had different name on the MIPS. Maybe it also had an interrupt, but here actually it will do interrupt service routine and call the interrupt by using the interrupt signal, the instruction. So there's an instruction called interrupt. And then once you call the interrupt with some type number, and then you will go to do different things depending on the interrupt type. So remember that our system call, we need to do what? We load the V0 with 4, right? Remember that?
Yeah.
That one actually is provide a type number. Same thing for the interrupt instruction in this 8059A. For CPU, you need to write something called interrupt instruction. And it's not called in MIPS, interrupt in MIPS. It may be called a system call or something. But it's actually similar. It's called software interrupt. Software interrupt is done by programmer. So like me, I write a Intel assembly code, and then I will actually issue the software interrupt by me. Hardware interrupt is done by system. System say, okay, now I need to read something from my hard disk. It's called hardware interrupt. So, okay, division by 4, I need to do something. You know what I'm saying? So hardware interrupt usually is something bad. You need to handle the exception in your assembly code level. So that's this one, Pentium 4 chip, and then Pentium 4 logic unit, logic pinout. So each CPU have the pinout. Pinout has this different kind of pin, as I mentioned. Bus arbitration, request, error, response data. Data is a pin, okay, for data input or output. And interrupt level, power management, heat management, clock rate, clock frequency, diagnostic, initialization, snooping. Snooping is for snooping bus. For snooping bus, whether to not related to write through or write back. I think that's more advanced. Not if your teacher doesn't teach that, I would just bypass it. Okay. So pipelining in Pentium 4 memory bus. So instead of just one cycle, finish the whole memory cycle, you actually can do the whole pipelining just like your CPU. So that actually better utilize the whole bus. Is that okay? So the Pentium 4 memory bus also have the pipeline in that your processor. Now actually overlapping different memory access cycle to make the performance of your memory better. Is that okay for this one?
Yeah.
I think this textbook actually has a lot of things, right? And UltraSpark. Okay, Pentium 4 and UltraSpark are different things. Who is using UltraSpark? Sun Microsystem. Okay, and Sun Micro now is actually dead. It actually sold to Oracle. So this one no longer there. Okay, Sun Micro was popular for a while, but it's done now. It's actually not important. Pentium series actually take over everything now. So UltraSpark, it's actually similar. You have these different level cache things, so you can study it. 8051, this one is early small controller. This one still widely in use. And this one actually is for those kind of like dishwasher, laundry washer, AC controller. A lot of microcontroller is using 8851. And still in use, okay? This processor is low cost, still in use. So that controller is a very longevity processor. So if you say, okay, so if you say 2018, there are still people teaching people how to write 8051 assembly code.
Do subscribe to eGrad channel and press bell icon to get updates about latest engineering, HSC, and IIT JEE main and advanced videos.
Hello friends. In this video, we will write an assembly language.
Is that okay?
Means those 10 numbers are
Okay.
stored from.
I don't know.
Still,
Yeah, it's okay. Don't need to understand it. I just show you like there are still people teaching people how to write 8051. So 8051 is a controller widely used in especially the smaller, not computer. It's used actually like it's really used to control the AC power. Is that okay? So a lot of controller project, especially tiny project, those things actually using many of the 8051. So it's a very successful long use model that actually room temperature control. Those kind of things actually use the 8051 because it's quite small and the chip is very cheap right now. The chip is very cheap right now. So a lot of controller just use the small 8051 controller for projects. Is that okay? Is that okay?
Yeah.
So that's one of the project. Good for project microcontroller project. ISA bus. ISA bus is a bus used for PC. It's called integrated system bus. It's actually used for what? The one you have the add-on cars, right? your memory card are add onto the ISA bus. So here, this one ISS bus is different from PCI Express bus. So you use for memory and maybe for hard disk. So this is something like this, you call ISA bus. And then you add those ISA bus with the video card or something. But this actually is already old, okay? This thing is already old. ISS bus is already old. Now it actually got replaced by PCI Express. I don't think there are quite too many ISA bus in newer PC now. Actually, this one is already out of date. And the PCI Express is used to replace the ISA bus. So actually, so right here, in the system bus, there is an ISA bridge. Okay, this one bridge is like the one I call it South Bridge, North Bridge. That's called bridge. So what is bridge? The PCI Express will go here and then go into the bridge, right? And then access the other one bus. And your main memory is over here. So there's a bridge between this side of I/O device and last side of I/O device. Is that okay? Is that okay?
Yeah.
A different type of the buses are connected through a different bridge. So here you have modem, sound card, printer. What is the nature of this side? This side actually is slower. As you can see, modem, sound, printer are slower. This side actually are faster. Memory, CPU, you see that? This side actually is faster. So here you have a PCI Express that actually used for high-speed railroad. This one is low-speed one. So low-speed connected to here so that you actually need to go through bridge to access the ISA bus. But ISA bus in the old days actually the main bus for I/O. But now actually got almost like retired. So here you have a Pentium 4, you have a bridge chip, and that bridge chip actually is what? The controller of your bus. Is that okay? And actually it's adds so many functions, so it become a bridge. And the bridging function is actually, you actually cut your I/O into several levels. Faster level, CPU, memory, local bus, cache, those are one level. Then the PCI bus for USB devices, and this SCSI devices. So here, even keyboard, mouse are connected to here. You know, so if you go through the USB channel, you will actually come to around here. And those soundtrack, like the one I'm talking to you right now, I connected to the audio jack, right? Those are ultra speed, low speed devices. Printer, those are slow speed one. Is that okay? They go into different level. So here you have the USB ATA PI hard disk. So this ATA PI is also out of date. Now it's called what? ATA PI now is called what? It's called SATA now. Serial ATA. Is that okay? It's called hard drive. It's called, now it's different name. It's called SATA. So the information in the textbook is no longer true. So in the past you have the IDE, you have the IDE hard disk, but now it's all replaced by SATA. That's a serial ATA. That's called serial ATA. Is that okay? And serial ATA is faster than the IDE. IDE hard disk is now almost gone. Nobody is using that. It is too old. So here ATA, SATA 3.3 6 gigabit hard disk or whatever. People are talking about this. Okay, so this one is old. Okay, USB 2 now old. We have the USB 3. Graphic, you go through the graphic adapter memory. So bridge chip, north bridge, south strip bridge. Try to set up these different bridges. Is that okay? And then bus arbitration now is like PCI Express itself. Say at this level you have PCI Express bus, right? And actually this guy will arbitrate who will get the control on the bus. Okay, that's the PCI Express arbitration. So PCI Express bus signal has so many different signals. Basically, it's still the same. Negotiating for the control of the bus, right? Send my address available, strobe in my address, and then enable my output or enable my input, and then put the data there. You know what I'm saying? Everything like that is a bus cycle. Everything like that, there is a bus cycle. So we can actually read something called PCI Express bus cycle. Okay? It's a bus architecture, and you can actually check the bus cycle. And if you search for the data like that, you will see what PCI Express cycle is, what a bus cycle, what control signal I need to send out, something like that. So here, this one, I will save it for you to study, okay? PCI Express, my card can send or receive data to my bridge. Okay, this switch is the bridge. And then connected to different things. So there are different PCI Express 1, 2, 3. Now it's PCI Express 3 already. So PCI Express starting from ISA bus. But ISA bus now I say it's too slow. Then PCI Express bus. Now it's PCI Express 2, 3. It's much faster now. Is that okay?
Yeah.
So your FPGA goes through the PCI Express buses. Here you have the CPU chart, system bus, you have the bus bridge, you have the chipset, you have the RAM, you have PCI Express bus. So this just tells you what are on the board of your CPU, your processor or motherboard. Okay, so this one, I think you can go through the different signal, but I don't think your teacher will be testing that. So here actually you just think about your CPU connected to cache, and that actually has a bridge chip connected to the memory. And that bridge chip right now is a PCI bridge, right? And your networking USB, whatever is on the PCI bridge. And the ISA bus, I think still there, but probably only very low devices will be put there. And the next one is a USB root hub. So here I show you how USB data has been sent out. So each time you have the 4-pin, and then you send the data out. So there is like PIO for the different ports. This one similar to that. And then you have the different ROM address. Let me see what this is in the test book. So we finished this one, bus arbitration. Next one, bus arbitration, we finished that. And then Intel chip. Okay. The one I shown actually private Pentium 4 is 2.0. Okay. So the textbook now is using Pentium Core's i7 as example. So you can read this, but the name of the different chips. So the slides we have is actually Pentium 4, that's 2.0. So now it actually is like i7 core, okay? So i7 has all i7's own pin now, okay? And that actually you can read it, and then if you don't understand it, you can talk to me. But I don't think it's so much fun to test individual chip or bus at the detail level, and it actually probably making no sense, and then probably not theoretical. So there's a lot of different technical terms to learn. So this one, what the heck is this one? So busy. What's that? This is a system on a chip. So basically, it's an ARM7 processor. I mean, So this one is the ARM7 processor, probably used for cell phone or something. So the whole system on a chip. What is system on a chip? What is system on? That's the only thing you need to learn right here. Okay, the previous one we talked about a single board, right? You put your CPU, whatever, right, on a board. But now everything moved into a chip that's called system on a chip. Is that okay?
Wait, what did you say it again?
Okay, the previous motherboard, we have a CPU, we have the slot, whatever on a board, right? That's our PC, right? Our notebook has that, right? But now this one is called, we put the whole system stuff into one single chip.
Oh, okay.
System on a chip. So actually this is already available and many years already, maybe 5 years or 10 years already. It's called single chip PC. Okay, and it already been able to perform quite decent job. Only one chip. Of course, there are some I/O devices like controlling the USB or something. Other than that, the whole system basically is just now can be put into a single chip, tiny single chip that actually work like a computer. You know what I'm saying? Tiny single chip can work like a computer now. It's called system on a chip. And system on a chip right now actually is a trend in the future. So even the AI chip now try to actually do this. NVIDIA, memory bank, and then everything just put like this. Whole chip is almost like a system. No more motherboard. Okay? Okay, ARM chip. So that is coming, and this field called embedded system is one of the strong field for UC Irvine actually. So that actually is a lot of fun. If you want to do project in here, it's not bad. Okay, it's not bad. And what are they for? They actually build these different devices for embedded system. So that's called system on a chip. I don't want to waste time. So basically, you can use the ARM core to build a system on a chip, and then everything is on the same chip. So these are the new materials. So the slides may be too old. So Intel 80. This one is the AdMail. Hey, Eric.
Yes.
Remember this AdMail?
Yes, I remember.
Yeah. So this AdMail also sells these microcontrollers. Okay. AdMail also is a company that producing this microcontroller. But AdMail actually got acquired. The company is gone now. It's still alive. Okay. The operation is probably still there. I believe it's acquired by Microchips. Okay, it's just recent, okay, that 2 years ago. Microchip buy AdMail, okay, 3.6 million. AdMail is quite a good company, actually, in this domain, in this microprocessor domain. And it has its own fab. But I think the reason why eventually they sold the company is like their fabrication part is not good enough compete with ARM anymore. So their chip are good for a while, but eventually they actually, when they compete with the high-end embedded system, it is no longer as strong. Suppose the Core i7 and whatever it is ARM chip of high-performance computing platform designed to build in highly capable computing devices like cell phone, okay? And however, another whole wide world of computers exists, but actually far more pervasive embedded system. What does pervasive mean?
Pervasive, it's like spreading.
Yeah, separating. So just like the laundry type controller, AC controller, those kind of things. 8-mil are good over there. So they sell the low-end chip. So where? Small cell phone, personal organizer, microwave, controller, camcorder, VCR, laser printer. Is that okay? That's what 8-mil good at. So that's why eventually it's sold through the company called Microchip. And then it has the CPU, EEPROM, whatever, same thing as well. So it also has the architecture. So when you actually got a project, say embedded system project, when you got an embedded system project, so someone asks you to do a board design, right, and a whole say AC controller. First, you need to know about the chipset and the CPU chip. What are the instructions? What kind of programming I can do? That's one thing. Second, you need to know about the system spec. What are the memory size? What are the I/O channels? Okay, what are the devices I will do? Get keyboard, my printers, or USB, something like that. Okay, after you got those analyses, and then you start to think about what is the computing I need to do. Okay, what is the computing I need to do? I need to bring out the system, load some program into there. After that, I need to load something from my PROM, right? And after that, I need to do my AC, right? So I will have a while loop, keep listening. Okay, temperature up or down. Should I turn on my AC with more power or tune down? Something like that. Those controller will have a main program over there just to operate the need for the embedded system. Is that okay? So based on that spatial computing purpose, embedded systems for that. So the purpose of having this different chip spec or architecture over here is to teach you what are the chips available, high-end, low-end. The most high-end is the CPU, like Intel processor. Middle end is the ARM processor, mid processor. Low end is this ML processor to meet different embedded system need. Is that okay? And then talking about PCI Express, what's that for? That's actually is for what kind of device I can add into my system, and also when I build a board, what material I need to have to build a board, and if I upgrade my board, how can I do it? You know what I'm saying? Those kind of things. And then here is the HS decoding. I think I teach you this already, right? HS to the select stroke. So that part is okay. So we pretty much finished this one, chapter 3 up to here. Let me check if there are more things. I think there are a lot of reading for you as well, okay? There still are a lot of things to read right now for you as well. So example buses, you have PCI Express. So there's quite many details. But right here, I just teach you some basic principles. And at the end, we have the interfaces and HS decoding. We finish that. But you still need to study the textbook, okay? And work on the homework. Okay, that's it for today. Thank you. Bye now.
Bye.